Okay, off we go. Hope everybody had a good break. Hope everybody's well rested. Hope you had a little bit of a chance maybe to look at a little math. So ideas stay fresh in your mind. But anyway, here's what it is. Don't forget about the attendance quiz and attendance code. I know it's easy to get out of that habit, right? So make sure to get that done. Clock's ticking, of course. And back into it we go. So last time we were talking about surface independence. Right? And the short version of surface independence is that it's just like path independence, just one dimension higher. Everything one dimension higher. But other than that, totally analogous. A great way to see this is to look at the diagram. Reminder that this is the diagram that I like to use. It's again, it comes from really natural and sophisticated and powerful tools that were used to study these ideas 80 or 90 years ago, I forget exactly, and boiling off all the formalities and abstractions and stuff that doesn't really affect, leaving only rubber meets the road. How does this affect us in Math219? And this is approximately anyway, what you get. And remember, path independence we talked about as follows. It pertains to certain vector fields. These are the vector fields that are gradients of something. These are vector fields for which the curl is 0. These are vector fields such that if you look at any two curves that have the same boundary points, you get the same value for the line integral. Right? And by the way, how did we show that every gradient is path independent? We used the fundamental theorem of line integrals. You can look back in the notes to where we did that. How did we show that a path independent vector field can be detected by its curl being 0? We used Stokes' curl theorem and that argument. And again, you want to go back to where we made that argument. So, when we say that surface independence is the same thing, just one dimension higher, the whole argument shifts just like that. It's literally the same exact pattern. So surface independent vector fields are those when you have two surfaces with the same boundary curve, give you the same flux. They happen also to be the vector fields that are curls of something. They happen also to be the vector fields whose divergence is 0. How do we know that divergence equals 0 is the test? Gauss's divergence theorem is the way we concluded that. How do we know that curls are path independent? Stokes' theorem is what proved that for us. So the pattern is insane. It's crazy how strong the pattern is, and again, this will reduce your sort of memory load. Right? How much do you have to remember? Do you have to remember various different theorems, or do you just have to remember the one pattern and realize that that pattern applies, wherever you happen to be looking? By the way, likewise, if you're in 2 dimensions, same pattern, everything works. Okay. Alrighty. Okay, so let me leave that there and going back now to here. Oh, and let me go full screen here. Okay, so let's see an example of this in action. We'll look at this example here. The statement of the question is this right here, and as I've commented many times, notice that questions like this do not announce themselves as, this is a surface independence problem, or this is a divergence theorem problem, or this is a Stokes' theorem problem, right? It just says compute the flux, right? And so you've got to figure out, this is how the real world works, right? Someone who asks you to compute this flux are asking you because they themselves don't know how to compute the flux. Right? So you've got to figure out which of your appropriate tools will work. Now, when you're looking to compute flux, there are several various different options, and we know the divergence theorem sometimes allows us to compute flux. Maybe that's how you do this problem. We know that sometimes Stokes' curl theorem might allow us to compute flux. Maybe that's what we should do. Right? Various different candidates to consider. And of course, there's also, every so often, sometimes I don't want to minimize this possibility. Sometimes you just have to parameterize and plug and chug, right? Pull back through the parameterization. So a lot of different methods. Okay. All right. So I'm going to take this vector field and observe that if you compute the divergence, indeed you get 0. An easy calculation to do. And noting that the divergence is 0, and reminder, our diagram, when the divergence is equal to 0, right, among these equivalent conditions, that means that I can use surface independence. How are we doing? Everybody okay? Everybody with me? Yeah.
Can you explain the second part of what you said?
One more time.
Can you explain the second part of what you said?
The second part, so when we compute the divergence and when we get 0, the punchline is that we can use surface independence. Is that what you were asking? Okay. Yeah. Right. By the way, now there is another. Let me just observe while we're here. Right. If you compute divergence and get 0, that also tells you that your vector field is a curl of something. That means that Stokes' curl theorem is on the table. You could use Stokes' curl theorem, or so you might think. And here's the problem. If you decide that, okay, hey, this vector field, it's a curl of something, I can totally turn this thing into a line integral, right? The problem is you'll need to know this F. You'll need to know the vector field whose curl is your given vector field. Said differently, you'll need to take your vector field and find its anti-curl. Perhaps you've noticed that term doesn't sound familiar. We've never talked about how to find an anti-curl, and that's because it's hard. There isn't really a good method that I can show you. So in a case like this, Stokes' curl theorem is, it applies, but I'm going to say it's not really a good option because we don't know how to find the anti-curl. For your consideration, there are some situations where the anti-curl is something that you can notice. That happens sometimes. I've got an example coming up. I may or may not be able to get to it today, but there will be an example that you can look at that will show that happening. Okay, but what we're going to do here is we're going to say, okay, divergence is 0. We can use surface independence. Let's do that. So surface independence. Let's remind ourselves what that means. Here's the surface we're given. It's this upside down paraboloid, just the part above the XY plane. We need to find another surface that has the same boundary as this one. And then we can throw this one away and just use that new surface. Is that cool? All right. Let me show you a landmine. We're in a dangerous situation here. It's easy to mess this up. I've seen the following happen many times on student papers. What I have drawn here to represent my surface is very similar to what I would have drawn if I were interested in describing this solid in here, which is very similar to what I would have drawn if I were interested in this surface combined with also this surface. In other words, if I were looking for the boundary of this solid, the pictures all kind of look the same, right? So it's easy to accidentally confuse yourself by your own picture, right? And it's very, very important to see the difference between all of these things. So in particular, let's take a careful read of what this question says. S is part of this paraboloid. Hopefully you recognize from chapter 2, this is an upside down elliptical paraboloid, right? Remind yourself if necessary, but upside down elliptical paraboloid. S is part of that paraboloid. This business over here about z being greater than or equal to 0, this is a clarification of which part I'm referring to, but it remains. S is part of the paraboloid. Right? This business down here is not part of our surface. Does everybody see that? It's real easy to get this wrong. Now, what a lot of students might think is, okay, well, yeah, but I've got this thing, and then when I cut, the cutting, that defines this sort of bottom side thing, and that's a surface too. It is a surface. It's just not part of this one. I hope everybody's good with that. Anyway, I wanted to point out this as a point of confusion. If you are still not entirely clear what the difference is, why isn't this bottom piece included? That'd be a great question to come talk to me about after class. Keep in mind we have office hours right after class. I'm happy to help out. Okay. All right, so we need another surface that has the same boundary. Let's talk about the boundary. The boundary of this surface is going to be this ellipse right here. Now that's a geometric appeal. If you look at the picture, where is the edge? That's where the edge is. We have to worry about orientations. Orientations are important. This surface that was given to us is oriented downward. Keep in mind what that means. That means kind of like this. Alternatively, you might call this inward. It's not as good a term. Technically, there's not a closed surface. There is no inside. There is no outside. You might call this oriented toward the z-axis. That would be reasonable. Make sure to realize, though, that when this says downward, we do not mean straight down. That is not on the table. That is not that's not even a normal to the surface, right? So again, careful with the terminology. The terminology's job is to distinguish unambiguously between the legitimate options. It is not intended to be a precise description. Okay. All right. So when we say that this purple curve is the boundary of this oriented surface, which orientation do we pick on this purple curve? We got to get that right because orientations matter, and the new surface we're going to pick has to get that same orientation. Right hand rule. We've got a surface orientation. Remember, thumb goes in the direction of the surface normal. Fingers of the right hand curling as they like to do toward the palm, etc., etc. Toward the z-axis, you see my fingers in my right hand. The swirl will be, let me zoom in so we can see better. There we go. The swirl will be kind of like that. And now imagine as I drag this picture, as I drag like so, that swirl is going to come down there like that, and that side swipes in that direction. Right there. Is everybody good? Everybody happy? Yeah.
If the S was oriented outward, then would the boundary be counterclockwise?
It would go the other direction. That's right. Yeah, absolutely. Yep. Okay. So there's our orientation. Now remember, when you're going to use surface independence, once you have established what the oriented boundary is, all you need is to pick any new surface that has that same oriented boundary. We no longer need the old surface. Just for dramatic effect, I'm going to go ahead and erase all of that. I have no further need for the originally defined surface. I can now pick any surface I want. It's outrageous, right? It almost seems too good to be true. I can pick any surface I want, as long as it has this same oriented boundary. And when you can, a fabulous choice. If there is a flat surface that has that boundary, I don't want to say always. There's obscure weirdo counterexamples, but it's going to be hard to argue against this in most cases, right? So I'm going to pick this flat surface here as my new surface. And again, we just got to play boundary games. I have to decide which of the two possible orientations on this new surface gives me that same boundary. Everybody happy? Everybody on board? So let's consider the options. I'm going to do the wrong one first, because once we get the right one, it would seem particularly silly. What if it were going upward? If this surface were oriented up, thumb, fingers, swirl, the swirl would be going the wrong way. So that's wrong. Everybody good? All right, well, the process of elimination, we know the answer, but let's see it anyway. If we orient downward, per that formula, thumb, fingers, swirls, the swirl would be going like so, which is correct. How we doing? Everybody good? Okay, so again, I was originally asked about this green flux. We've cited surface independence. Surface independence tells me I can instead look at this blue flux. That blue flux is easily rewritten because the normal vector, I have a formula for, the vector field, the original vector field, I have a formula for, and it's easy to do that dot product. Nothing to it on the dot product. That leaves me then with, let's see here, let me get rid of we're done. See, we're even done with that now. We're just looking at a flux through that surface of, not a flux. We're looking now at a scalar surface integral of negative xy on that surface, and I claim that there is a symmetry argument that will allow you to deduce that zero. And I'm going to leave that as an exercise for y'all to fill in, flashbacks to chapter 5. And make sure you can do this. Make sure you can think through for yourself what plane or planes might be reasonable choices by which to make a symmetry argument. And I'll give you a hint. There's two of them that work just fine. Do keep in mind you need this integrand to be odd through reflection through whatever plane you pick, and you need for the domain to be symmetric through whatever plane you pick. Think through those details. And a reminder, on an exam, you have to say equals 0. You have to say by symmetry. You have to indicate the plane that you're using. And you have to be right. In other words, there has to actually be such a valid symmetry argument. Okay, so a point being here that this difficult question that would have been tedious computation devolves into sort of unravels into a triviality. And great way to solve this problem. Pausing for questions. Everybody all right? All right, now, real quick, I'm going to address a mistake that this is a tragic, total landmine situation. Some students will see this integral and say equals triple integral of divergence equals triple integral of 0, because after all, the divergence is 0, and then they get 0, and they even get the same numerical answer, and a lot of students are convinced that this is a fabulous argument. And this is a tragedy. Nothing that's written in red relates to this question. It is a total coincidence that they happen to numerically get the same answer. And the problem, again, very tempting, right? A lot of people would, what's wrong with that? That looks pretty good at a quick glance. The reason this is nonsense is the very first thing that got written down here, right? This hypothetical student's trying to use Gauss's divergence theorem, which does not apply because this surface is open at the bottom. It is not a boundary. Because this is not a boundary of any solid, there is no solid for this triple integral to be defined on. There is no such triple integral. This is meaningless nonsense. It absolutely doesn't work. This is, again, a real tragedy. Everybody see the problem there? Questions, feel free. I want to make extra sure we take every possible precaution, hoping no one will step on this land. Everybody good? You got to be really careful if you're going to apply the divergence theorem. Make sure that your domain, make sure your surface is a boundary. And a good way to check yourself and make sure you're thinking that through is to indicate clearly what is the solid whose boundary you think is your given surface. And then again, make sure also that you correctly interpret what the surface is. Okay. Yeah, and just to be clear, I am going to go ahead and put a big X through all of that. Okay, moving along. Here's a related method. This is more trouble to implement. When surface independence it works, I think surface independence is the better method. It's quicker. Ultimately equivalent when surface independence applies. What's nice about surface closing that I'm about to show you by example is that it applies even when the surface, even when the vector field is not surface independent. So this is a more powerful method, but it's clunkier and harder to use. Okay, here we go. Let's suppose that we are interested in computing a flux through, get back to highlighter mode. This surface here. Now again, be extra sure to carefully read and interpret correctly what the surface is. It makes a huge difference that this surface that we're interested in is just the portion of the sphere, right? It does not include this disk at the top, right? This is not a closed surface. This is a wide open surface, like an open bowl of cereal, right? It is not. There is no saran wrap across the top. Is that cool? Everybody with me? Okay. So, wouldn't it be nice if we could use the divergence theorem? Can't. It's not a boundary. I know it's not a boundary because it's not even closed. But here's the slick move. This surface that I'm given, if I were to combine it with this other surface, not part of my original surface, but if I were to combine it with this other surface, D, between the two of them, and carefully orienting, let's see here, orienting that one that way, and orienting S as we're supposed to, oriented downward. Between the two of them, I literally am looking at the boundary of this solid that's contained on the inside. Everybody see that? Okay, so let me emphasize this boundary. That is the boundary of the solid on the inside there. Okay, so now what I'm interested in, it remains that I'm interested in S, right? But I do at least have a boundary on the board, and hey, maybe that might be good enough in some way. And here's how we can make it good enough. First, we notice, and I'm going to get rid of the color coding here, by the way. So I just need to recover my colors. This equation tells me this, right? The fact that S and D combine to make the boundary of H, well, that's really just what this says. This is just saying let's take the flux through both sides of that equation, the same equation basically. And then notice this one is literally a boundary, and therefore I can write down the divergence theorem. Let me do like, try to get this all on the, there we go. So the divergence theorem kicks in. It still doesn't tell me what I want, right? We gotta, keep track of what's going on here. What I want is just that thing way over on the far left. But nevertheless, the divergence theorem is working, and what I'm interested in is involved. And sometimes that's good enough. So here's how we put it all together then. I look at that equation, and we compute, keeping in mind that that's what I want. I can compute the flux through D easily because D is flat. It has a super convenient normal vector that I can just look at. Look at 0, 0, 1. It's a constant. It's loaded with zeros. That's an awesome normal vector. I love that normal vector. And again, this blue computation here, pretty straightforward. And then furthermore, this computation, the triple integral of divergence, easy. Because we have a not such a bad solid there, and the divergence is constant. Now the divergence isn't 0, but the divergence is 3, as it turns out, and 3 is pretty easy to deal with. So there you go. This by closing the surface, by taking my original surface S, by adding an additional surface in order to make it a boundary, invoking the divergence theorem, etc., I've related the thing that I'm interested in to the blue integral and the red integral, both of which are easy. And therefore, simple subtraction, and I can compute what I'm actually interested in. That's a slick move, right? It's very clever. Very clever idea. And can be useful in various different circumstances. And notice surface independence would not have worked here because the divergence is not 0. This vector field is not surface independent. But this surface closing works nicely. Everybody all right with that? All right, just a couple of quick comments on how to use this. This is a nice exercise. I want to encourage everybody to do this right here. Persuade yourself that if the divergence is 0, this method of surface closing is truly equivalent to surface independence. So think that through. It's a good little exercise. Once you see it, it's pretty straightforward, but it's a good realization to make. And so you can see now why this is a generalization, because again, this method works even if the divergence isn't 0. And then, of course, since you are going to have to compute a triple integral as part of this process, you want to make sure that divergence is easy to work with, right? So you can kind of eyeball glance your vector field and just look at that divergence. If the divergence is going to be something ugly, where this doesn't look like it's worked nicely, then it's probably not a good choice. All right. Well, if I remember correctly, we are now done with the new material of Chapter 7. Everything that follows is supplemental. And this page here, you'll recognize these diagrams. This basically is a reminder to myself to come back here and make sure that we've talked about this diagram thoroughly enough. And we've already kind of done this at the start of the lecture, but make sure you're really comfortable with the idea that this pattern, the equivalence of these 3 properties, the green, the orange, the blue, regularity issues aside, these are a simultaneous property. The exact same vector fields have all 3 of these properties. Right? So when the divergence is 0, you have surface independence. If your vector field is presented as a curl, you don't need to compute the divergence. You know it's 0. If you know the vector field is surface independent, then you know that there is an anti-curl. Cool stuff like this. Very handy. And remember, there's a whole bunch of analogous statements that you can say about path-independent vector fields, but you don't need to memorize those as a whole separate list of various different properties to know. Just know it's the same pattern. Right? If you organize all these ideas in your mind in the sort of the framework of this diagram, you don't need to know that whole additional list of properties. They're all the same. Everybody good? All right. Okay, so let's see here. Back to the notes here now. So again, we are kind of done with chapter 7 at this point. I do have these additional supplemental examples. The idea here is that computing line integrals and surface integrals is kind of a big deal. That's a lot of what we do in this class, certainly in chapter 6 and 7. Which, by the way, the math department had a detailed, frank conversation with the Pratt School, right? About, okay, what does Pratt most want its students to know about multivariable calculus? And they were very emphatic: vector calculus. Second most important thing being vector calculus, etc. Right? They could not have been more emphatic. This is the big stuff. So how to compute these line integrals and surface integrals is a really big deal. Here is my compact executive summary. Here's how you do it. Here's how you compute these things. First thing, make sure you know where you are in the diagram. It's immensely helpful, right? The diagram doesn't help if you don't know where you're. A map doesn't help if you don't know where you are on the map. I don't know if y'all thought that little reality. Like, you can't just have a map and, oh, there I am, right? So you got to identify for yourself, where are you on the diagram, and then do what the diagram says. The diagram will tell you to compute some appropriate operator for the vector field you're interested in. Do what it says. The diagram will suggest specifically for you to think about the boundary of whatever domain it is that you're looking at. Think it through. And then as a result of doing both of those, there will be certain consequences that you can conclude. Think those through. Right? So you want to explore exactly what you've got, exactly what that means, and exactly which options are on the table. And once you have all those options in front of you, then you can just pick, okay, well, what's going to be the best? What's going to be the most convenient way to do this? And then while you're at it, head on a swivel. Watch out for geometric good fortune. You get lucky sometimes. You'd be surprised, again, how often you get lucky, right? You got to take the freebies when they come. And likewise, always be on the lookout for symmetry arguments. And again, it's really nice when that happens. Okay. Here is an example, first example. By the way, these 6 examples that I have that are the remaining 6 pages of these this part of the lecture notes, these are the supplemental. I have been doing them for several years now, including during the COVID semesters. And in I think it was the first COVID semester, I recorded standalone recordings, just not in a classroom, just, sitting alone in my office at home, right? And I made detailed recordings of everything I could think of to say about all 6 of these examples. So we're going to do what we can with these for the next 16 minutes, and then after that, I'm going to refer you to those recordings. I'm going to put them up on the YouTube channel so you all have convenient access to them, and I strongly encourage that you watch those to your satisfaction, because there are pretty cool examples and a lot of neat ideas that come up in these. So anyway, let's see what we can get done. And here we go. The question says to compute a line integral. Step 1, where are we on which diagram? What are we doing here, right? It says compute a line integral. By the way, notice we're in 3 dimensions. The vector field has 3 coordinates. our parametrized curve, another dead giveaway. 3 coordinates. Right, so we're in 3 dimensions and we're looking at a line integral. That means that this is what I'm trying to compute right here. In R3, vector line integral. Several things are immediately clear. One is this vector field. Diagram says I should compute the curl of that. So we're going to do that. We're going to follow the advice that's going to end up working out really well for us. So anyway, notice how the diagram's telling us to do it, right? The diagram says, if you want to look at a vector line integral, well, that vector field, that integrand, apply curl, see what you get. We're also going to think about the curve. Specifically, we're going to think about the boundary of the curve, and by boundary of a curve, we mean the starting point and the ending point. And a couple of different things we can include about that, too. Okay, in fact, let's start with the curve. Okay, starting with this curve. What I'm going to observe about the curve, first of all, it's super ugly. I don't want to try to draw a realistic picture of this. That seems super duper hard. I don't think that's going to be helpful. Okay. What I want to decide is whether this is a curve that is an open curve, or perhaps instead, is this a curve that is a closed curve? Every curve is either open or closed in this sense. And notice, curves that are open are not boundaries. Curves that are closed are boundaries. Right? Okay. So how do we tell the difference? Well, the way we tell the difference is we're going to take the starting value of t, plug it in, and see what our starting point is. Whatever that starting point is, I don't know. And then we're going to take the ending value of t, we're going to plug that in, we're going to see where our ending point is. And the ending point will either be different from the starting point or it'll be the same as the starting point. Right? So this is an easy little computational hack. Now we're looking at this hack because this curve happens to be parametrized. If the question had been given differently, if the question had been, maybe the curve was described in some other way, it might be perfectly obvious just from the statement of the geometry that the curve either is or isn't closed. But in this case, we need the help because it sure is hard to tell by looking. And you can compute these points. And by the way, here's the easy foot in the door. Let's just look at this component, the third component. Clearly, we get different values for t equals 0 and t equals 1. This is clearly an open curve. This, therefore, is clearly not a boundary. And what that tells us, there is no anti-boundary surface. So Stokes' theorem is not an option. Don't even think about using Stokes' theorem. Can't use Stokes' theorem. It's not a boundary of a surface. There is no anti-boundary surface to even propose working with. Everybody good? All right, now let's do the curl. Again, it says right here, it says compute the curl. Okay, so back we go. Let's see here. Let's compute this curl. I'm going to get rid of, might just get rid of all of that. Let's compute the curl. Now this is a computation, and y'all can check me on the details of this calculation. Make sure that you're proficient, right? Quick, reliable, get the right answer every time as quickly as possible. That you can compute curls, and this curl in fact is 0, 0, 0. Make sure you can do that. Okay, so what does that tell me? Well, back to the diagram. I got 0. That means that there is an anti-gradient. That means that the fundamental theorem of line integrals is a perfectly reasonable option. After all, what would prevent me from being able to apply the fundamental theorem of line integrals? The only thing that would ever stop me is I might not have an antigradient. This says I definitely have an antigradient. Go for it. How we doing? Is everybody all right? Notice the diagram has told us what not to do, and it has also told us what we can, and for lack of better options, probably should do. Right? It's just use the fundamental theorem of line integrals. And I suppose, now here's another option, I suppose you could use path independence. The problem with path independence in a case like this is, well, I would need to parameterize a new path, and I would still have to parameterize the path and plug and chug, and that is going to be, I think, probably more work doing it that way. Generally speaking, if you can find an antigradient, I think that'll be easy here. By the way, it's another thing. Make sure you can do that. Make sure you can find the antigradient here. Remember, we have a nice little hack, little game method for finding the antigradient. These are just polynomials. It's an easy game to play, easy game to win. Play that. So when the fundamental theorem applies and when you can reasonably find the antigradient, use the fundamental theorem. Okay, is everybody happy with this one? The details I'm going to let y'all fill in. All right. Okay. Next example. So again, context. Where are we in what world? Well, we're in 3 dimensions, and we're computing a line integral. So that's the same place we were last time, so I'm going to kind of retain a lot of this. You know what? Before I do that, let's see here. How do I... let's see. Oh, there we go. Okay. Back to the last example real quick. Let me just remind you, and I've said this previously, but I think this is a really good observation. When you're computing one of these, this is the world that's relevant to you. I strongly advise don't go around computing divergence of that vector field. It's a bad look. Divergence has nothing to do with the question. Right? So what some students do, and this is just a strategy that's probably been either encouraged or possibly even taught in high schools, is shotgun style. Compute everything you could possibly think of. Whenever 2 Legos fit together, you do it, right? And so a lot of people would say, I was given a vector field. Let me compute the curl. I'll compute the divergence. And what else can I think of to compute for this end, right? And they just compute everything under the sun because, hey, who knows? Maybe it might be relevant, right? I don't know if that sounds familiar, right? I got explicitly encouraged to do this when I was in high school. This is a bad piece of advice for a college math class because it's not about the answer, right? We talked about this a million times. It's not about the answer. It's about when we read everything that you write and try to get inside of your head, what does it look like you do or don't understand? Right? If you, as this would suggest, if you compute the curl only, that suggests to me that you realize what we have, you've got a good lay of the land, you understand how the diagram works, you understand the context. Right? If you then furthermore compute divergence, well, that's irrelevant, and furthermore, if you compute both curl and divergence, I can no longer conclude that you understood something about curl. You see what I mean? So you can actually hurt yourself. And again, in high schools, they tell you that there's no such thing as I don't know, I got taught in the high school, like in preparing for the AP exam, don't worry about writing something down that's wrong, it'll never penalize you. Well, that doesn't make any sense. Of course, you can make yourself look bad, and you want to try to avoid that. Does that make sense to everybody? Okay. So don't compute the divergence. Don't write down any triple integrals. Right? If you're trying to compute a line integral, very bad look. Don't put the word Gauss anywhere. Let's see here. Don't talk about any 3-dimensional solid. Just stay away from the extremes over here that clearly have nothing to do with what we're computing. Okay. There we go. Okay, so back to here, 3 dimensions, line integral. So again, we are here in the R3 diagram. We're going to take our vector field. We're going to compute the curl. We're going to take our domain. We're going to think about its boundary. Here we go. Okay, let's look at the curve first. Starting value of t, ending value of t. See what you get. R of 0, R of 1. And arithmetic, I'm going to let y'all do that arithmetic, and I'll just cut to the punchline. These are equal. So what we have here, we have a curve that starts at one point, and then by this formula, it sort of cruises around and does a bunch of stuff, and then, wouldn't you know it, it ends up stopping back at exactly that same point. So we have ourselves a closed curve. That means this curve is a boundary of a surface. I don't know what surface, but this is the boundary of a surface. And so back to the diagram, the boundary is 0. There is no boundary, right, because it starts and ends at the same point, and therefore there is an anti-boundary surface. Stokes' theorem is on the table. Everybody good? All right. Okay, let's compute the curl. Again, I'm going to let y'all do this. By the way, this is one that you can do in your head. You get 0. The way you can do this in your head is, remember, curl is computed by 6 different partials. There's only x's in the first coordinate here, in the first component, right? And of the 6 different partials, only 2 of them are going to be done to this thing, and they're going to be the y partial and the z partial, which are therefore 0. Likewise, only x and z partials of this thing. Only x and y partials of this thing. They're all 0. So this is, at a glance, curl equals 0. Is that good? Which means that we got 0. Oh, hang on. We got 0. So there is an anti-gradient, and I can use the fundamental theorem of line integral. So, and let's not forget that we had this option too. So we have 2 good options. Again, we're not going to say a word about divergence. We're not going to mention anything about any triple integrals, right? Steer clear of the bad looks. And we have a couple of options to choose from. By the way, it turns out both of these options are excellent options. Let me show you how they both go down in this case. Move this up here. Let's see here. So option 1, if I were to use Stokes' theorem, I'm going to have a flux through some surface of the curl of f dot ds vector, which is a flux of 0, which is therefore 0. And this seems too good to be true, because, hey, wait a minute, I never established what this surface is. I've got a wacky curve here. What if this surface is, the nightmare of trying to figure out that surface? It doesn't matter. Because through this unknown nightmare of a surface, I'm computing a flux of nothing. No flow, no flux. At the integral is 0. Is that cool? All right, let's see the second way to do this. Second way to do it, as it turns out, also really nice. I can cite the fundamental theorem, and I get f of r of 1 minus f of r of 0. Now we have another nightmare here. Oh my gosh, I'm going to have to figure out what is the little f right? How do I take the anti-gradient of this oh my God, I'm going to have to take an x anti-partial of that first bit there. That's integration by parts twice. Yikes. And then even worse, I'm going to have to take a z anti-partial of e to the z squared. I don't even know how to write that down without like power series, and this seems like a nightmare. But here's the thing. The curl is 0. I know there's an anti-gradient. It's super ugly, but I know there's an anti-gradient. I know that this f exists. And I also know that these 2 points are the same point. So it kind of doesn't matter what f is. I'm going to be looking at the same value of f minus the same value of f, and this, therefore, again, I get 0. So it's just kind of beautiful how this works out. That analogously to the fact that I don't even really need to know this surface. Likewise, I don't even really need to know this function. I need to know they exist. That's very, very important. I got to know they exist. I don't need to know what they are, just because of how everything else has worked out. Everybody happy? Okay, call it a day. We're going to do all of chapter 4 on Wednesday. Believe it or not, it's not even going to be hard, and we'll be done with the class. So see y'all on Wednesday. Have a good one.